Thank you. So, I don't know if you've noticed, but I think this presentation consumes the least amount of space on the disk. So it should be the easiest to follow, I hope. You could see it on the folder listing. I think it's okay. So, but you can hear me, right? Now. Okay. So, no, I do have pictures, but they're vector graphics pictures. So I'm going to talk about art gallery theorems. This research and results are joint work with Erwin, who's sitting in the front row. So, what is the art gallery problem? Very broadly speaking, to cover a geometric object using guards of prescribed power, prescribed visual power. And an instance of that is the point guarding of orthogonal art galleries. So, the gallery is a simple orthogonal polygon that is a closed polygon with no self-intersection and whose edges are axis parallel. We want to cover this, the inside of it, using point guards, which have 360 vision. And the objective is to use as few of them as possible. And this is a covering problem by nature. Yeah, so a typical theorem would be to give you the minimum number of attainable point guards as a function of the number of the vertices of the gallery. And this theorem has been proven, a sharp theorem has been proven by Kahn, Klave, and Kleitman in 1980, which says that n over 4 guards are sometimes necessary and always sufficient to cover the interior of a simple orthogonal polygon of n vertices. So as you can see, you need to put a point guard for each tooth of this comb. And since every new tooth requires 4 new vertices, this result is sharp as well. And the proof uses convex quadrilateralization of orthogonal polygons, and it uses deep geometrical insight. Now, we want to avoid that. So a natural question would be, since we're working with orthogonal polygons, whether the theorem that n over 4 guards are sufficient to cover the gallery would still hold if the vision of the guards were restricted. And the restricted vision that we want to use is the so-called rectangular vision. So 2 points, x and y, in the gallery have our vision, or rectangular vision, of each other if the rectangle, the axis parallel rectangle that they induce, is completely contained inside P, the gallery, and it also contains x and y. And Dury and O'Rourke independently proved that indeed the art gallery theorem for point guards of orthogonal polygons hold even with rectangular vision. And the way they proved it is that they proved this partition theorem of orthogonal polygons, namely that any orthogonal polygon of n vertices can be partitioned into at most n over 4, at most 6 vertex pieces. And it's clear that an at most 6 vertex orthogonal polygon can easily be covered by one guard. So this implies the theorem of Kahn, Klave, Kleitman, and it is a more general result as well. So this result and also other previous results point to the, existence of a meta theorem that art gallery theorems have underlying partition theorems. Okay, now let's consider now mobile guards in orthogonal art galleries. So what's a mobile guard? A mobile guard is an axis parallel line segment in the gallery, and this guard sees a point y in the gallery if there is a point x, or sorry, other way around. So the guard sees a point x in the gallery if there is a point y on its line segment which has rectangular vision of this point. So you can think of this as if the guard was patrolling the line. Now it doesn't have to, so it's not a problem if a point is not seen by any of the guards at a certain point of time. We only require that there is a time point for each point of the gallery when one of the guards sees it. Okay? So this orthogonal polygon can actually be covered by one mobile guard, even with rectangular vision. Okay, and so here is the art gallery theorem for mobile guards. It was proven by Agarwal in 1984, and it says that 3n plus 4 over 16 mobile guards are sometimes necessary and always sufficient to cover the interior of a simple orthogonal polygon. Now, O'Rourke realized that there are two interesting questions that are not answered by the proof of Agarwal, and one of them is that this proof does not guarantee that Agarwal's proof does not guarantee that the patrols of the guards are non-crossing. And secondly, it requires vision throughout the patrol of the line of the mobile guard, not just at the endpoints. So if we believe in the Mezei theorem, then we should look for a partition theorem behind Agarwal's theorem. And we believed it in firmly, so we were able to find it. And we proved that n-vertex simple orthogonal polygons can be partitioned into 3n plus 4 over 16 at most 8 vertex pieces. Now, why does it answer the previous two questions? Well, clearly, an at most 8 vertex polygon can be covered by one mobile guard, either vertical one, actually, yeah, or a horizontal one. So, since this is a partition, the fact that the patrols are non-crossing is trivial. And also, you only really need vision at the endpoints of the patrols. And the chain of swastikas that you're seeing on the board, on the slide, is just the sharp example that proves that this result is sharp, since if you draw another swastika, then actually it will generate 16 more points, and you need 3 more guards for each of the arms. Okay, so yeah, we've seen the results in the bottom row. I've also listed results for general polygons to reinforce my point. And so you can see that if we transition from point guards to mobile guards, we need three quarters as many guards. And now the second question that we studied with Erwin was whether this was only an extremal phenomenon, or does it hold for individual art galleries as well, individual orthogonal polygons as well. Seems to be hopeless. You take the comb again, and you can see that you need a point guard for each of the tooth, but actually one mobile guard can cover the whole gallery. However, we had the idea to restrict the mobile guards to either only vertical ones or only horizontal ones. Now there is a chance that these two numbers become comparable, the number of mobile guards and the number of point guards necessary to cover the gallery. So let P be the minimum number of point guards required to control P. Let M sub V be the minimum number of vertical mobile guards required to control the gallery, and let M sub H be similarly defined for horizontal mobile guards. And indeed, this 3/4 ratio appears again, and we prove that the minimum number of vertical guards plus the minimum number of horizontal guards over the minimum number of point guards has a ratio of at least 0.75, and this result is sharp. Here is the polygon that proves the sharpness of this result. So whenever you attach one more of these blocks, you need 4 more point guards, but only 3 more mobile guards. So I'd like to point out that simpleness of the orthogonal polygon, or simply connectedness of the art gallery, is essential. As you can see, we have k square, where k is equal to 3, black dots, and no 2 of them can be covered by 1 point guard. So we need at least k squared point guards to cover such a grid. However, the number of horizontal and the number of vertical guards needed to cover the gallery is only linear in k. So P can be as large as you want compared to, well, in terms of linear constant of mv plus mh. Okay, so a few words about the proof. The main idea is to construct the pixelization graph and translate this whole problem to the graph. So what's the pixelization graph? First, we cut our polygon at each reflex vertex vertically, and we get a set of vertical slices, which are rectangles of the polygon. This is going to be the bottom class of the graph. Similarly, we cut our polygon at each reflex vertex horizontally, and we get the set of horizontal slices. And now G is simply the intersection graph of these sets, meaning that 2 nodes are joined by an edge if and only if their interiors are intersecting. Yeah. And so with respect to rectangular vision, it doesn't matter where a point is or where the 2 points are in the gallery exactly. We only need to know they're containing horizontal and vertical slices. So the edge that contains them contains enough information to decide where the guard is in the gallery. So point guards are translated to edges in this manner. Mobile guards, vertical mobile guards, are translated to nodes. Similarly for horizontal guards. And now rectangular vision is tricky a bit. It leads to a very non-natural notion of covering. But so either 2 points share their horizontal slices, or the slices of 2 diagonally opposite pixels and the corresponding edges induce a C4 in G. And again, to go backwards, we need simply connectedness, because this C4 only guarantees that there is this C4 in the polygon, but the inside of it could be empty. However, since we know that P is simply connected, this cannot be the case. So indeed, these 2 points have rectangular vision of each other. Okay, and one more thing. So what is a vertical mobile guard system now? If each of the horizontal slices is intersected by a vertical guard, then it is indeed a covering system, a covering vertical mobile guard system of the polygon. And so you get that the systems correspond to subsets of the bottom class which dominate each vertex in the upper class. Yeah, so I mentioned that simply connectedness is very important. This property translates to the chordal bipartiteness of the graph, which means that any cycle of length at least 6 must have a chord. Now, unfortunately, the reverse direction doesn't hold. But this is more than enough for us. This is the main property that we use about the graph. Okay, I don't think this will fit now. Time. But so let me mention an application of this theorem. So if you rewrite the inequality, you get this inequality, and this value is not easy to compute. The best exact algorithms, as far as I know, have a running time of n to the 17. This was proved by Borman and Kyle in 2007. However, we proved that these two values can be computed in linear time. And so, via a trivial observation that m sub v is at most p and m sub h is at most p, we get that this number is actually an 8/3 approximation of the minimum size point guard system. And thank you for your attention, and I would gladly answer them.